speaker this morning, Sofia Covarrubias, has joined us from Cal State LA this summer. She's been working with Henrique, and she'll tell us about their project together, an updated line list for beryllium abundances in solar twins.
Hi, thank you, Glenn. So I'd just like to get started with some background. So the sun, okay. Okay. Yeah, the sun has provided us a case study for many of our questions about stars. And as much as we would love to apply our data from the sun to any star that we want, first we kind of have to apply that to solar twins. So solar twins follow a similar evolutionary path as the sun. They have a similar evolutionary track, mass, and stellar parameters. So from this line list, in order to ensure proper results, we do have a little bit of further constraints, and that's going to be our effective temperature and our surface gravity. And that's just because we're using the most up-to-date definition for what a solar twin is. So we know what's happening below the surface of stars by analyzing their elemental abundances. So stellar internal mixing brings photospheric material into the stellar convective zone. And once there, it moves through the interior via convection. Once beryllium and lithium reach the base of the convective zone, temperatures are hot enough to burn them. And then the material is brought back to the photosphere. And because they have different temperatures that they're burned at, they do come back in different amounts. And that's what we call depletion, and that helps us determine how much internal mixing has happened. Ooh, wrong way. Okay, so why are we looking at lithium and beryllium? Well, lithium, this is a graph of lithium abundances as a function of stellar age, and that's in billions of years. So here we can see we have a lot of different points. We have a lot of data for lithium, and it's pretty well correlated to each other. It follows, its own path. And each of these colored dotted lines are different models for internal mixing. And they all sort of agree with each other. But beryllium, on the other hand, we do not have nearly as many data points for. And it doesn't really follow any of the internal mixing models. And even if it did, there's just not enough data points for us to confidently choose an internal mixing model off of this. So what does this mean for us? So I'll be updating the line list on the area surrounding the transitions, the beryllium transitions at 3130 to 3130 angstroms. 3131 angstroms, and these are these two transitions right here, and I'll show these in more detail in a second. But this is the area that I'm going to be working on. And I mentioned line list. What is a line list? This is a small snippet of the line list that I was working on. So in this first column here, we have the wavelength that the transition happens at. Second column, we have what element or molecule is there. Third column, we have the minimum excitation potential, which is the minimum amount of energy required to get that particle excited. Fourth column, we have our log GF, how likely it is for that transition to actually happen. And that is going to be the column that I did all of my work on. And I'll talk about that a little more in a second. Our fifth column applies only to molecules. That is the dissociation energy. So the amount of energy required to break a molecule into its component atoms. And last, we have our data source. So okay, this line list comes from this Placco et al. Paper from a program called LineMake. But I am updating it with solar abundances from Asplund et al., except for beryllium, which I am using the absolute newest data from this Coretin 2022 paper. And in order, in order to update this line list, I'm using a program called Moog, which is a radiative transfer code. And what that means is that it assumes local thermodynamic equilibrium and a 1D model atmosphere. And it takes in 3 files. So my line list that I'm editing, a model atmosphere, and an observed spectrum to plot on top of. And from there, it calculates a synthetic spectrum, which I will show in a second. The observed spectrum that I'm plotting on top of comes from the VLT UVIS interferometer, which was taken from off of the Juno asteroid. And the reason we use that is because it takes the solar spectrum as a point source. So it's more easy to apply it to other solar twins, because whether we like it or not, we are going to be observing those as a point source. Yeah, so this is what Moog outputs. So this was the line list when I first got it. No changes had been made to it. And just for reference, here are beryllium transitions. It looks pretty bad. It's not a very good fit. Nothing really lines up. And personally, for me, one of the things that bothers me most is this area right here. And after a little bit of research, I found out that that was a theoretical iron transition that does not appear in observations. So what I did is I looked at this, I checked it against the NIST Spectra database. I said, this is a theoretical transition. Obviously, it does not appear in the observed spectrum of the sun. So I can go ahead and pull that out. And that's exactly what I did. And it looked a lot better. My next issue was differences in spectral resolution. So I mentioned that we did take this solar spectrum as a point source. That does have some effects on the resolution, but also, more importantly, our calculations can have an infinite resolution if we want them to, but that's just not how instrumentation works. So we did have to turn down the resolution a little bit just to make sure that it fit the observed solar spectrum. So after that, it was a lot nicer. And I just included this point because that was, an important result of the resolution. Yeah, and this is my final spectrum. So just as a reminder, these are where those 2 beryllium transitions are. Pretty good fits, if I do say so myself. But yeah, this is my final spectrum. And thank you. Just for reference, this is what we started with. And this is what we end with. And yeah, I'm very happy with my results. But as nice as this looks, what does it mean? So with an updated line list, we can create a synthetic spectrum capable of reproducing the areas around the sun's beryllium transitions. And this is important because if we can actually estimate beryllium abundances in solar twins, we can better understand their internal mixing. Yeah, that's all I have.
All right, very nice. Questions for Sophia?
So you said you choose lines between 3130 and 3131 angstrom. So why do you choose those certain lines?
Yeah. So I'll just go back here. So yeah, this is that area. And I just worked on this because this is the area surrounding those 2 beryllium transitions. And that's really what we want to focus on. We want to focus on beryllium abundances because we don't have as many data points as that. And if we can get those beryllium abundances in solar twins, yeah, we can get more data to understand how internal mixing works. But I hope that answered your question.
Yeah, so in one of the slides, you show kind of like a lot of data that comes from MOOC. And you said that you only selected one of those columns. Yeah. Can you explain more about like why you kind of disregarded the other ones? Even though like it's like dissociation energy, that sounds important, and like wavelength that the transition happens. So yeah, can you explain more about that?
Yeah, great question. So these, you're right, they are very important. And that's kind of why I didn't edit them. So this minimum excitation potential and this dissociation energy, I can't really edit because that would be sort of like editing like elemental definitions, which I don't want to do. So what I did is edit this log GF, which is how likely it is for the transition to happen. And what that does, I'll show you the spectrum. So what that does is it actually moves my synthetic spectrum up or down to, to fit the observed solar spectrum. And so by editing how likely it is for that transition to happen, the line will just move up or down and will fit the observed solar spectrum. And so that's the wrong one. I did edit these against the NIST spectral database just to make sure that these values were as up to date as possible. If there was experimental data, if there was theoretical, kind of like I mentioned for iron, I could change it a little bit. But yeah, I just wanted to make sure that like everything was as correct as it could be. And if it was theoretical, I could go ahead and change that.
I'm curious about the theoretical label you put on this one line. All these transitions are theoretical. By this, do you mean that it has never been observed at a star? And if so, is there any explanation for why this line is not observed?
Yeah, great question. So I personally did not put the term theoretical on it. So what I did was I checked it on the NIST Spectra database. And basically from there, they said that it was theoretical. It was just sort of calculated. And yeah, so it wasn't actually observed in the solar spectrum. So yeah, I was able to just kind of take it out. But yeah, I didn't personally put the theoretical like label on it. That was something that was kind of already documented. So hopefully that answers your question.
All right, let's thank Sofia.